Dr. Ranjani Parthasarathi is a professor in Department of Computer Science and Engineering. Her area of specialization is in computer architecture and computer networking. She had guided more than 5 PhD students and currently guiding 5 PhD students. She had published paper in more than 50 national and international journals. She worked in many sponsored projects and she got IBM Faculty Award for 2008.
Welcome to the UGC lecture series in computer science. We are looking at a series of lectures in computer networks. Today we will be looking at the network layer. We have already looked at the lower two layers, the physical layer and the data link layer. Now we will be looking at the network layer. So in the network layer, what are the functions of the network layer is the first topic that we will take a look at. Then we will look at one of the functions, which is switching. And under switching, there are three different methods that we will look at. One is circuit switching, the other is packet switching, and the other is virtual circuit switching. So let's look at the position of the network layer in our network layer stack. So if you look at the position of the network layer, it is placed between the data link layer and the transport layer. So it gives services to the transport layer and receives services from the data link layer. Remember that this is our 5 layer or 7 layer protocol stack model. In the TCP IP model, this will be, you will have the data link layer here and the transport layer on top. The same thing is true of the OSI model as well. So network layer is in between the data link layer and the transport layer. The functions of the network layer are the following. You will have internetworking, packetizing, addressing, routing, switching and forwarding. So let us look at a little bit of this in detail. So the duties of a network layer are these, right. So what is meant by internetworking? You need to connect up different networks. So we have different networks which need to be connected. We know the different nodes can be connected by a network by means of some local area network. But when you have different local area networks to be connected, then we talk about internetworking, and this is something which is done by the network layer. Then we talk about addressing, which is identifying a node in a network. That is, you need to be sending data from one network to another and from one node to another node in that network. So an addressing mechanism is required to make sure that you are able to identify a network and within that network a node. So we need an addressing mechanism that also has to be handled by the network layer. Third, we need to be looking at routing, switching and forwarding. You can, what is meant by routing? Routing is to identify a path from a source to a destination. Switching and forwarding refers to actually forwarding the data, whether it is in whatever kind of switching mechanism is used. How do you actually forward the data when the data comes to the switch? So that is something which is to be handled. And if we are looking at a packetizing kind of a network layer, a packet based network layer, then packetizing also becomes another important duty of the network layer. So now let us look at switching first. So what is this switching? In switching, okay, switching in general refers to just connecting up two things, right? And any switch basically just connects up one end to another end. So what kind of switches do we have and what kind of switching mechanism do we have in networks? So we talk about circuit switching and store and forward networks. So what do you mean by circuit switching? In circuit switch, you have a connection that is established from one end to the other end. A typical example of a circuit switch is our telephone network, where before you make a call, before you actually start talking, a physical circuit is established between the speaker and the receiver, the person on the other end. So that is what we mean by circuit switching. In store and forward networks, it is a different class of networks. Here what we do is we use something called message switching, packet switching, or we use something called cell switching. So what we do here is a message, a packet or a cell, which is a smaller packet kind of a thing. Now these are sent from one switch to another switch. It is stored at that switch and then forwarded over to the next network. In packet switching, of course, we have further divisions. We can have a connection oriented or a connectionless approach. A connection oriented packet switched approach is called as a virtual circuit network, and a connectionless network is called as a datagram based network. So these are the different types of switching mechanisms which are possible. We will take a look at each of these in detail. If you look at a circuit switching network, an example as I told you is a phone network. So what is it that is done first? First you establish a connection. That is, a source creates a circuit to the destination. That is, you have a circuit, a physical circuit that is connected between the source, from the source to the destination, and the nodes along the path store the connection information, or in other words, the nodes reserve resources for the connection. Okay. And when a data transfer has to take place, the source sends the data over the circuit that has been established. Now, when the data is transferred, no destination address needs to be specified since the nodes know the path. After the connection has been transferred, connection has to be broken down or tear down takes place. Source will then tear down the circuit when it is done with the data transfer. That is, the source requests that the connection can be removed or the connection can be broken down. Now, if you look at the timing of data transfer in a circuit switching mechanism, so let us just take a look at this example here. I have a host 1 sending data to host 2 via 2 switches. So, typically what would happen is the first you have a circuit establishment phase where a circuit establishment request is sent all the way through the network. So, the request goes to switch 1 does some connection establishment over here and then sends the request to switch 2, that establishes the connection on this side, sends it to host 2, and host 2 on receiving the connection request sends back the information. Now, you can see that there will be a transmission delay and a plus propagation delay for this connection establishment request to take place. So, the connection establishment as a whole has a certain delay. After this, data can be transferred. Now, note that there is no other delay here, you just keep transferring the data. Once you finish with the data transfer, then you break down the connection, the circuit tear down takes place, which again will have a delay which is almost equal to that of a circuit establishment phase. Okay. So, this is the overall timing of a circuit switching mechanism. See that there is a delay before you can actually start transferring data. Okay. This is what happens in a circuit switched mechanism, but once you establish a circuit, data is transferred continuously. Now, when you have this kind of a circuit switching mechanism, you can see that a link on a particular link, there could be different circuits which can be established. That is, a link can be shared to establish different circuits. So, how do you exactly allow this sharing to take place? So, this is done by means of the technique of multiplexing, which we have already seen. So, if you look at multiplexing, we can see that we can do time division multiplexing, in which each circuit is allocated certain time slots. So, you can see that they are all different time slots which are allocated, and one circuit can take different time slots. Or we could do frequency division multiplexing, where each circuit is allocated certain frequencies. So, if you look at, so for instance, the blue color is a different frequency, green color is a different frequency, and so on. Different frequencies are allocated to different channels or different circuits, and all these transfers can take place simultaneously. So, you can see here that you are limited by the number of frequencies that you would have, and here you are limited by the number of time slots that are available in terms of accommodating a certain number of circuits. So, the number of circuits that you can accommodate in both these cases, time division and frequency division, is fixed. So, let us look at the advantages of this circuit switching mechanism. One of the first advantages is that you have a guaranteed bandwidth. So, what we mean by this? Now, when you have a guaranteed bandwidth, you can say that so much of data transfer can take place at any given point of time. So, you have a predictable communication performance, and it is not just a best effort delivery with no real guarantees, as happens in the case of packet switching and other networks. The next advantage of circuit switching is that you have a simple abstraction model. There is reliable communication channel exists between the hosts, and no worries about lost packets or out of order packets and so on, because once you have the connection established, you just send data at one end and it is just received correctly on the other end in the same order in which you sent it. So, it is almost like a pipe, you just pour something at one end and data comes out at the other end. So, there is no question of packets being lost or data being lost or out of order and so on. The third advantage is that the mechanism is a very simple mechanism, and at each switch what needs to be done is a simple forwarding, and it has very low packet overhead. Now, forwarding is based on just the time slot of frequency depending on what mechanism you use, and there is no detailed header on each packet, which obviously means that the packet overhead is low. And as a consequence of that, there is no need to inspect a packet header, because the forwarding is just based, since you already established the circuit, you are just going to continuously send in the data. So, these are the advantages of circuit switching. Now, coming to the disadvantage of circuit switching, one of the first disadvantages is that you have bandwidth wasted bandwidth. Now, why does the bandwidth get wasted? Now, if your traffic is bursty, it could lead to idle connection during the silent period. That is, I have established a connection, but let us say I am not transferring data continuously, my traffic is bursty, I send data for some time, then there are idle periods. Now, during this idle period, during the silent period, the connection is idle, nobody else can send data on this particular channel, because you have dedicated this particular circuit for this connection. Therefore, you are unable to achieve gains from statistical multiplexing. Now, in statistical multiplexing, remember that we would be able to multiplex data from different connections. In this case, you cannot do that because you have a dedicated channel that has been allocated. Another disadvantage of circuit switching is that you can have blocked connections. That is, Again, connection would be refused when resources are not sufficient, and it's not possible to just offer some okay service to everybody. You're going to give service only to some people, but to them you will be able to give a guaranteed bandwidth. But the fact that you're not able to actually entirely utilize the full bandwidth and the connections could get blocked is one of the disadvantage of the circuit switching mechanism. Also, there will also be a connection setup delay which happens. Now you can see that no communication can take place until the connection is set up. So if you're just having small data transfers, you will still have that initial connection setup delay. So you cannot avoid the extra latency for small data transfers. This is another disadvantage of the circuit switching mechanism. Another disadvantage is that you need to maintain network state. That is, the network nodes, the routers or switches that we talk about, must store the per connection information. That is, for every connection that is established, they need to store the status of this particular connection that has been established. So you are unable to avoid the per connection storage and the state. So you need storage for every connection that needs to be established. This is another disadvantage of the circuit switching mechanism. Now coming to the store and forward networks. Now here this is different from the circuit switching mechanism in the sense that intermediate processors, intermediate nodes, routers, gateways or switches along the path store the incoming block of data. And then what do? Each block is received in its entirety, inspected for errors and retransmitted along the path to the destination. This implies buffering at the router and one transmission time per hop. This is the mechanism that is used in all the store and forward networks. Now let us look at what happens in the first mechanism in this, which is message switching. In message switching, this is essentially a store and forward network where the block of data transfer is a complete message. So since messages can be quite large, this can cause buffering problems and high average delay. So you can see why this is so, because you are going to receive a complete message and then transfer it onto the next link. So you need to buffer the entire message until then. So the average delay that you have could be quite high in this case. Okay. Now coming to packet switching. Now what is a packet switched mechanism? Again, it's a store and forward network where the block of transfer is a complete packet. Now what's the difference between a packet and a message? Basically a message is a meaningful complete unit, but this message now can be broken down into some packets, some small sized packets. So a packet and the size of this packet can also be variable, it need not be fixed. So a packet is a variable length block of data with a tight upper bound. What do you mean by tight upper bound? All we are saying is that the maximum packet size is typically fixed. So you have a tight upper bound. Now using packets will improve the mean message delay, that is the time taken to send a complete message will be lower in the case of packet switching, because you are splitting it up into smaller size blocks and you are sending it. Okay. So the average time that it takes for you to receive a packet, store it and forward it becomes less. So that's the advantage that you have with the packet switching over the message switching mechanism. The next mechanism that we have is cell switching. Now in cell switching what we do is, here the unit of data transfer, that block that you are talking about, is very small and it's typically a fixed size block of data, and this is what is referred to as a cell. Okay. So when you start switching cells, naturally you get much faster rates of data transfer, and the ATM network, which is the asynchronous transfer mode network, it typically uses this cell switching mechanism. So this uses 53 byte cells. Note that the size of each cell is really very small. You have a 53 byte cell. In fact, this has about 5 bytes of header and 48 bytes of data that are being sent. And since you have fixed cells like this, fixed size cells, you can actually use hardware switches which can work really fast. So with cell switching you can get some very fast circuit switching, cell switching mechanisms. Now coming to our packet switch networks, which are the most commonly used networks, let us look at some details of this packet switch network. Now when we talk of packet switch networks, we talk of connectionless protocols where no setup is needed, and each packet contains information which allows the packet to be individually routed hop by hop through the network. This is one option that we have. An example of the connectionless network would be something like this. You have this is an example of a network here. So I have data coming in from 1, which is a source, to the destination 2, which is another host. So now data can go through multiple paths. Now you can see that there are multiple networks here and multiple routers that it may go through, and finally it will reach the destination. So this is an example of a connectionless internetworking mechanism that can take place. So we will just take a small break and come back and continue with what we have been looking at. Welcome back after the break. We've just been looking at how the connectionless datagram approach works in the packet switch networks. So let's just take the look at this example again. So I have a picture here of 4 packets coming in from A and which are to be sent to X, which is the destination. These here are the routers, the pink ones here, and you can see how data could be the different packets which belong to the same connection, same set of data transfer, that is packets going from A to X, can actually take different paths. So let's say for instance the packet number 1 takes this path, right, it goes over here, takes this path and comes over here. Packet number 2 may take this path, 3 may take this path and 4 may take a straight path through this. So now you can see that the order in which the packets are received at X can be different from the order in which they are sent. Possible that one is received first, followed by 4, then that is followed by 3 and that is followed by 2. Now the order is different not only because they are taking different paths, but it could also be because there could be different delays on each of these paths. So you can see that because of the different delays that you have and the different paths that are taken, packets in this datagram approach, which is the connectionless delivery mechanism, the packets could be received out of order and they could be delayed. So now let's just look at a quick comparison between circuit switching and packet switching. Now in circuit switching there is an initial delay because of a connection setup, and you have dedicated bandwidth in circuit switching. We have seen this already, but because of the dedicated bandwidth you could also have wastage of bandwidth, but you will be able to provide better quality of service because you have the dedicated bandwidth, and also circuit switching provides reliable connection. Now coming to packet switching, let us compare each of these points with respect to circuit switching. Now in circuit switching we said we have an initial delay because of the connection setup. Now in packet switching that does not exist because there is no connection setup. Now on the circuit switching side we have a dedicated bandwidth, whereas over here you have a shared bandwidth. Now since the bandwidth is shared, you have better utilization. Now why is the bandwidth shared? Because you are not dedicating the connection, different packets could come from different nodes and all of them would be simultaneously processed through the network. So you have a better utilization of the bandwidth. So even if there is an idle period from one connection, on one set of data transfer, that idle period would be used by somebody else to transfer data. So there is no dedicated allocation of bandwidth. So you have a better sharing of bandwidth. So you have better utilization on the whole. But what about quality of service? In circuit switching you are able to provide quality of service because of your dedicated bandwidth, whereas here you cannot provide guarantees. So no guarantees, but you have better sharing of or better utilization of the bandwidth. And there we talk about reliable communication, here you get unreliable service. So these are the basic, this gives you a basic comparison between circuit switching and packet switching. Now because of unreliable communication, what we mean is we could have packet loss, you have delays and you have out of order delivery of packets. So all these have to be contended with when you are looking at packet switching. Okay. Now but when we look at data transfer, for the kind of characteristics of data transfer which typically happens to be bursty, we find that packet switching offers us a better overall performance in spite of the fact that you have unreliable data transfer. Now when you have unreliable data transfer, it automatically means that we need to do something about providing reliability, so which is handled typically at a higher layer, but at the network layer, even if you go for a packet switching mechanism, you are able to achieve good sharing of the bandwidth mechanism, of the bandwidth that is available. Now coming to the third mechanism, which is our virtual circuit switching mechanism. Now in virtual circuit, this actually is a hybrid of the packet switching approach and the circuit switching approach. So what happens here is circuits are established, so you have a circuit establishment and tear down along the end-to-end path, and you use packet switching in the sense that data is divided into packets with identifiers. So we are actually trying to use a combination of circuit switching and packet switching. The difference is that in circuit switching you will physically establish a circuit between the two ends, whereas in virtual circuit switching you do not physically establish a connection, but you have a virtual kind of a connection which is established, which means you make some reservations at the intermediate switches, but no dedicated or no physical circuit actually is established. And when the data is sent, it is actually sent as packets. So that is, you divide the data into packets and send, and there is some kind of an identification in the data that it belongs to a particular virtual circuit, and that information is sent. So let us look at what happens over here. So if you look at the virtual circuit, now the packets will carry a virtual circuit identifier, now which associates that particular packet with the virtual circuit that has been established. Now this virtual circuit identifier will also be used to determine the next link along the path, and the intermediate nodes will maintain some state about the virtual circuit. So essentially it will look like a forwarding table entry which also has some allocated resources to it. Let us look at how the circuit establishment takes place. Now the circuit establishment takes place by means of something called signaling. Now what is the signaling? It is basically creating the entries in the forwarding tables, so that when the actual data gets transferred, you could just consult these tables and just send the packets along. And when you do the signaling, it also helps to reserve resources for the virtual circuit if needed, and this can also help to provide quality of service or some guarantees for the data transfer that takes place. Now when you establishing for establishing the circuit, we use two different approaches to signaling. Now one is what is called as a static approach, in which the network administrator configures each node. The other approach is a dynamic approach, in which the source will send a setup message along the path, and only when it is going to send data, it sends up the setup message, and when the setup message is sent, a connection will be established, a virtual connection will be established. Okay. Now when you do this, again you can see that as in the case of circuit switching, there will be a setup latency, because you require some time for the setup message to traverse the path and return back to the source. Then you have routing, of course, needs to be done, that is the end-to-end path is selected during this circuit setup. So remember that routing refers to identifying the path that is to be taken, and this identification of path, it could have been done earlier and be available as a routing table, but using that routing information, the end-to-end path is selected during the circuit setup mechanism. Now let us look at how an example of how this virtual circuit identification actually takes place. So let us look at this figure. Let us say for instance I have a connection 1, which is the red color over here, and another connection 2, which is the blue color, light blue color connection that I have here. Now let us say I have packets coming in from connection 1 and connection 2. Now between these two switches here, I have a single link, link 7. This link 7 is to be shared by both this connection as well as this connection. Let us look at how that is going to happen. Okay. So now let us say connection 1, which is coming on 1, has to be sent on link 7, and at this end it has to be sent on link 14 here and link 8 here. So you can see that what is coming on 1 goes through 7 and is sent on link 14. Similarly, what is coming on 2 will go on 7 and go out on link 8. Now we need to differentiate the packets coming from 1 and 2 on link 7, and how is that established, or how is that achieved? It is achieved by means of what we call as these virtual circuit identifiers, or VCIDs. Okay. So these VCIDs are something which are identifiers which are given when the source is set up, right, that is when the connection is established for the virtual circuit. And what the switches will do is they will map this VCID to an outgoing link, so that the data transfer can take place correctly. And packet, of course, we know is the fixed length label in the header. And the packet will have a fixed length label in the header which identifies this virtual circuit ID. Okay. So now let us look at what is happening over here. You can see that packets received on this particular link are transferred on this same link number 7 and transferred out on 8 and 14. So let us look at the swapping of the label at each hop. Now there could be a problem when you use the same number, that is the same number 1 on this link 7 for both the connections which are coming from 1 as well as from 2. Okay. So look at what happens here. If I use the same VCID along the whole path, each virtual circuit consumes a unique ID. That is, I will have to use a unique ID for the entire path. Now I do not know what are the different connections that are there on switch 2, but I have to determine earlier that on switch 1 I am going to use the same virtual circuit identification number. Okay. So what could happen because of this is it would start to use up all of the ID space in the network. That is, if I am using a virtual circuit identifier of say 8 bits or 16 bits, I only have a 256 or 2 power 16, 64,000 entries available. So now I would use up all this space because of different connections that exist between different networks. Now to avoid this, we use what is called as label switching or label swapping at each hop or at each switch. So let us look at what is happening here. You can see this example here. So what I do is, what comes on packet number on the virtual circuit 1 is transferred on to link 7, but it takes a VC ID of 20. That is, an ID of 1 here is transferred to an ID of 20 here. Now when this 20 ID comes over here to switch 2, it is sent out on link number 14, with an ID of 78. So you can see that there are 3 different virtual circuit identifiers that are being used over here. Now one is the identifier that is used over here, it gets switched to the ID 20. Now 20 is the VC ID that is carried on link 7, and when 20 reaches here switch 2, that is automatically switched on link 14 with an ID of 78. So when if I have a receiver B here, it actually receives 78 as the virtual circuit ID, but it is the same packet which is coming from here, from the source here, with a virtual circuit ID of 1. Similarly, what is coming on 2 is sent out on link 7, but with a virtual circuit ID of 53, and what is received as 53 here is sent out on 8. So these virtual circuit identifiers are the ones which are actually helping us to identify that this belongs to a different virtual circuit and needs to be sent out on link 8 and not link 14. So this is the virtual circuit switching mechanism that is actually used. So you can see this swapping of the label that is happening at each of these hops, as I just explained. So you can have something coming on 53 here going out as 42 on link 8. So these are the different swap mechanisms available. Now at each switch, so what actually will be done is you will have this label swapping take place, and which essentially maps the VC ID to a new value at each hop. The table will have old ID, will have 3 entries basically. It will have the old ID, the next link to be taken, and the new ID, right. So by using this table, the switch will be able to make this switching of the labels for every packet that is received. Now we can see that virtual circuits are similar to datagrams in certain respects and different from datagrams in certain. Let us look at the similarity first. Now as in the case of datagrams, data is divided into packets. So that is, sender divides the data into packets and the packet has an address. Now in packet switching, it will have a complete address, whereas here you have something called a VC ID which is used to uniquely identify that particular packet. Now both of them use store and forward mechanism, that is, multiple packets may arrive at once. So you need some buffer space for temporary storage, which is not required in the case of circuit switching, but this is different over here. Similarly, multiplexing is done on a link. That is, you can have multiple packets from different virtual circuits going on the link. Similarly, multiple datagrams going on the same link. So there are no reservations done in that sense. So it uses statistical multiplexing, and packets are interleaved without a fixed pattern. Now reservations are done for resources done for group of packets, which is what happens in virtual circuit. Whereas, so you are able to provide some amount of guarantee, because you can have guarantee get a certain number of slots. This kind of reservation is provided on virtual circuits, whereas that is not there on datagrams. Now whereas do virtual circuits differ from datagrams? In the forwarding lookup. Now virtual circuits, you use a fixed length connection ID, so that is what is required for doing the forwarding. Now in datagrams, the full destination address, for instance the IP address has to be used for transferring the packets. Okay. Now again, another difference with respect to virtual circuits is that when you initiate a data transmission, virtual circuits must signal along the path. So you need to set up the circuit, whereas IP datagrams you just start sending the packets. So no initial delays. Another difference with respect to the router state, in virtual circuits router must know about the connection, so some state is established, whereas in datagrams no state is established, so it is easier to recover from failures. Quality of service, again you can see that virtual circuits resources and scheduling are done per VC, so you are able to provide quality of service, whereas it is difficult to provide quality of service in the datagram networks. So to summarize, what we have looked at today essentially is the primary switching function which is used at the network layer. So we have looked at 3 different switching mechanisms: the circuit switching mechanism, packet switching mechanism, and the virtual circuit switching mechanism. We have also looked at advantages and disadvantages of each of these switching mechanisms. A few questions for you to review the content of what we have studied today. Question number 1, what are the functions of a network layer? Question number 2, what is circuit switching? Question number 3, what are the advantages of circuit switching? Question number 4, what is packet switching? Question number 5, can data be lost in packet switching? Why or why not? Question number 6, what is virtual circuit switching? Question number 7, why is the VC identifier important? Question number 8, why is VC label changed at the switches? Question number 9, what is the switching technique used in A, telephone networks, B, internet, C, ATM networks, D, X.25 networks? Thank you.